Just a little bit about Altair. We want to empower our users to create better products faster, and we do this partially through the Altair Partner Alliance. Only Altair offers its customers the benefit of using specialized software such as Maplesoft on demand and at no additional cost. Engineers who work within the HyperWorks platform can download and use dozens of additional applications by drawing on their pool of HyperWorks licensing units, just as if they were working within the core HyperWorks platform. It's easy to join the APA. All you need is a HyperWorks 12.0 or higher lease license. Register on our website, and once you're approved, you can begin downloading and using all of our partner products, including Maple and MapleSim. If you'd like more information, our website is altairalliance.com, or you can email us at apainfo@altair.com, or also feel free to visit the partner website, maplesoft.com. Today's presenters will be Orang Vahid, Director of Application Engineering, and Abtin Athri, Application Engineer at Maplesoft.
Hello, everyone. So the topic of our presentation today is virtual prototyping and dynamic load analysis in machine design. I'm joined here by my colleague Abtin, and we are going to be talking about model-driven innovation, the use of solutions from Maplesoft. This presentation starts with a quick introduction of Maplesoft and Maplesoft engineering solutions and discussion about model-driven innovation. Then I hand the presentation to Abtin, who will do a in-software demonstration of a reconfigurable robot model and some analysis of that. Then I will take over again and talk to you guys about a case study that we have done, a project that we have done with FLSmidth US, and then some concluding remarks and this presentation. So Maplesoft has been around for more than 30 years. It got its start from a research project at University of Waterloo, Ontario, Canada. The company was founded in 1988. And Maplesoft is now a leading provider of high-performance solutions, symbolic computation, and numerical computation used in academia, science, engineering, and mathematics. We have a global presence. The headquarters is in Canada, but we have offices in the US, Germany, UK, and Japan, and more than 30 independent resellers and partners worldwide. The focus of this presentation in the machine design topic will be the two softwares, our engineering solutions, Maple and MapleSim, and also our engineering services. So the challenges that are faced by engineers in design of complex systems are many. Multiple subsystems interact together in a big system that has to be correctly analyzed. There are multiple design groups that are in charge of each subsystem, and they need to communicate with each other. And these are often in multiple different domains, and different tools are used to address that. For mechanical and dynamics is one tool, electrical is another, hydraulic is yet another. And the challenge is when these subsystems come together, then as we have seen from discussing with our customers, that some problems show themselves after the integration. So being able to put together these subsystems in an environment, in a multi-domain environment, would bring positive results sooner in the process of design. So model-driven innovation. The solution for this complexity that are faced by engineers and designers is system-level multi-domain modeling. We start with simulation. We create a virtual prototype of the system. The system will capture the dynamic behavior. It can be used for design validation. And since multiple domains can be put together, it has the benefit of bringing all those subsystems in the single environment. And one can see 3D visualization of the system in action and explore different scenarios for the operation of the system. But doing the simulation is just the first step. Now that we have a system, we want to be able to do design exploration. We want to be able to easily tune the parameters, even do batch analysis, such as optimization, Monte Carlo, or parameter sweep, doing sensitivity, looking at vibrations, the result, signal processing of those results. Mechanical system often require doing inverse kinematics or dynamics, and looking at the equations. So once we have the model, these design exploration is also a need that needs to be addressed. Now that we have done our analysis of the system and found the right parameters or come to a configuration that is addressing all the design requirements, what comes next is the control and verification, being able to generate code that for controllers or hardware-in-the-loop applications, these code needs to be in real time. And there are multiple usage of being able to create code from the system. And connectivity becomes important. So a model-driven approach delivers design insight and not just simulation results. How we go about at Maplesoft to address these needs with our flagship product, Maple, and also MapleSim. Maple is a design exploration tool. It's a symbolic and numeric computation environment which gives you live mathematical documents that you can interact with equations, do parameter analysis, and do optimization. MapleSim is the system-level modeling and simulation environment, a physical simulation environment that allows you to drag and drop blocks that represent physical subsystems and connect them together in multiple domains. And from that model, after you have done your simulation, you can create code for hardware-in-the-loop or software-in-the-loop applications. These two softwares come with a variety of add-ons to expand their coverage, such as driveline library, battery library, tires, hydraulics, control, and global optimization on the MapleSim side, and also connectors to export the code that MapleSim generates through the use of Maple into other platforms, such as MATLAB or DSpace or LabVIEW, and many others. On top of these, Maplesoft engineering solution provides services towards creating models, doing design verification or validation, motion control and model predictive control analysis, hardware-in-the-loop code generation, and also training. So bringing all these together, we have MapleSim for creating the physical-based simulation models. This is the environment that we will be spending a majority of time in this presentation, showing you models that are created to address the machine design and loading issues. Then we use Maple for parameter analysis and optimization, looking at the design exploration, looking at a system model in MapleSim and changing its parameters and rerunning the system and comparing the results to come to a design decision. And of course, once that is done, then the connectors come into play to create code for real-time or other type of applications. And in the center of that is the professional services and the application engineering group that bring these all together and give you the fastest time to be productive and get your projects up and running. Okay, with that very short introduction, I am going to pass the presenter to Optin, who will take you through a demonstration of MapleSim and Maple. And this demonstration focuses on a pick-and-place type robot. Optin, you should now have the...
Sure. Thank you, Orang. As Orang mentioned, I'm going to cover an example of the simple mechanism design based on the industrial pick-and-place robot. And during this example, we're going to answer to the questions such as, what is the proper motor sizing for my robot? And what if I vary some of the link parameters, and how does that affect my robot configurations or design. And also we will go over some related bearing calculations, such as the loadings. So first, let's take a look at the simulation results. And here we can see the animations of the robot, which is fairly doing the simple operation. So as you can see here, we are dealing with 3 rotational motors and 1 end effector, which is following the desired trajectory. So for better visualization of what these motors are doing, I have put these components on top of this revolute joints. And as you can see, if I rerun my animation, you can see these motors are spinning in the highest speeds. And by help of the high ratio gears, we can achieve this accurate trajectory or path tracking at the end effector. And at the end, we have the prismatic joint, which is taking care of the pick and place action here. So going back to the, and also I have the access to the information of my robot components. So for example, here for all 3 motors, I have the plots for torques versus the speeds, which are showing the characteristics of these joints and motors for me. And also I have the different angles all plotted under one plot versus time. So let's first go back to the model and look at the structure of this robot. So as you can see here, we have the end effector, and then we have the link structures, which is connected to our sensor components. So using these sensor components, we can capture the variables or information such as the radial and axial force at each joint, in addition to the bending moments. So this information are going to be useful for all further analysis. And then we're going to have the revolute joint, which is providing or allowing for the degree of freedom at each joint. And these revolute joints are actuated using the motor subsystems. So if I go through this motor subsystems, you can see I have a position driver, which is going to dictate whatever position or desired trajectory or position I'm going to send in. I'm passing it through the gearbox, which is here the simple ideal gear component from MapleSim libraries, and then driving that revolute joint. Now, if I want to, or if I have more data like the positions and then angular velocity or accelerations, I can replace this simple position driver with the components such as the move component, which is accepting all these 3 inputs. So back into main level, we can see this configuration of the motor revolute joint sensors and links are again repeated for our second link and then the base link. And at the end, we have the base platform of our robots. So this model also contains the inverse kinematic solutions for the position tracking. As you can see, this block is created allowing for the parametrically accessing to the length of the 2 different links. So the L1 and L2, which are these 2 links. And then we can also have the second solution of this inverse kinematic. And as you have seen in my animation, I had the first solution. Now I can go and select the second solution and rerun the simulation again. And when the visualization window gets updated, it automatically pops up. And we can see this time the elbow link is going to point outward from the screen, which was inward in the previous run. So right now we are generating the visualization data, and This time you can see the elbow is pointing outward. And I can play this. Still, we are achieving the same trajectory. So the task or the pick and place action is the same as the previous one, but we are using the second set of solutions for our inverse kinematic. So this is the quick way of analyzing and then exploring your model outputs and your motor's characteristics. However, we can use the more powerful analysis tools, which can be any of our pre-engineered Maple templates or the user customized template, which I have one attached to this model. So if I go here and open up my analysis worksheet, you can see now we are in the Maple environment, and this Maple worksheet is already connected or attached to that MapleSim model, and this preview window on top of here can confirm that for us. So by clicking on the Simulate button here, we can it automatically connects to the model, run the model, and get the variables and results back to our Maple. And then we can do some further analysis and look at the systems information, such as the motor characteristics or the other data. So it's done, and over here under simulation results, I have the ability to change my information, which I'm interested to look at. So let's say for joint 1, I want to look at the angle. So you can see the angles are plotted in radian, and then I can look at the velocity of the same joints and also the accelerations. For example, here you can see these high spikes regions in the acceleration, which might be the good target for machine design process, and maybe you want to start investigating this and somehow smooth out these spikes by changing the configuration of your robots, or either the way you are actuating the those revolute joints or bearings at the point. What else we can see is like a bearing axial forces or radial forces, as I mentioned. You can see here. And then we have a feature to detect the minimum, maximum, and RMS values of each of these data sets. So I can turn on and off these values, and they're going to be shown as a line in my plot. So the next is the specific plots, which we're going to look at for our motor characteristics. So these data points are showing the performance of the operation for different motors at those 3 rotational joints. So for example, the motor number 1, motor number 2, and motor number 3. And again, here we have the access to minimum, maximum, and RMS values of these motors. And now let's say we want to overlay this experimental data from our simulation results with the data available from manufacturers. So what we first need is to, because we are not caring about the direction of the rotation of the motors, so we can easily take the absolute values of this experimental data or data point. And now we have this, we can load the external data files. So in this case, I have an Excel sheet attached to my model, which I can load it here, and then select the motor, which in this case, I'm going to go with the small motor, and then the small motor max. And I can display this plot. So these envelopes are showing the green one is right now showing the normal operating characteristics of the small motor. And we can see the joint number 1 or the experimental data for motor number 1 are exceeding these expectations or limitations. So if I turn on the maximum motor capacities, still we are exceeding this. So if I go to the joint number 2, we can see now we are better match for this joint. It's still, in some regions, like here, we are going to the maximum motor characteristics, and which, depending on the applications and based on the manufacturer's recommendations, might require more additional cooling for that motor. So this might not be the proper solution or solution to your application. So let's take a look at the joint number 3. And the motor, the small motor, which we have selected here, is the perfect match for that. And everything sits in the normal operating characteristics of that motor. So I can turn off the maximum limitations, and we are good to go for this. So if we go back for joint number 2, maybe in our motor list, we can choose another motor which also matches with that, which is the medium motor. But for joint number 1, still, I believe the large motor is going to cover most of the operating characteristics within the normal operation envelope or region. But still, I believe we have some points in the boundary, which means we have to go with the larger motor, or we can change the configuration of our robots to match for this motor. So next is going to be an iteration in another iteration in design process, which is considering the bearing life. So the bearing life of the robots are also very important. In this section, what we have is looking at the dynamic loads which are going to be tolerated or applied to these bearing loads or joints. Sorry. Able to measure the bearing forces and the moments, which we have this capability in our model by employing those sensors. We can look at these all 3 joints for the radial loads and the moments. So you can see here we have kind of the repeated cycles and repeated type of the spikes, and you can see these 2 set of spikes are distinct from each other. So if we go back to our animation and we replay the animation, we can see at these endpoints, or these 2 extremes, are exactly where our end effectors are moving up and down, and that's where we are experiencing these spikes. So we can also improve this by changing the way we are actuating our prismatic joints, and the way we are, or again, changing some characteristics of our motor to lessen these spikes. And next can be the way, let's say you're using the more sophisticated tools to look at the life cycle of the bearings, or calculating more loadings of the bearings. We can export all this data to the as a list, or in this case, we are going to do it into the Excel files. So I'm going to dump all this information as a file called temp on my desktop. And if I go to the desktop, you can see here we have this Excel file. And here on the first row, we have the titles of each information, or the probe data of our robots, like bearing 1 radial force or axial force, and so on. And then underneath, we have the corresponding information or the values based on the time. So this can be exported, as I mentioned, to any other tools for further analysis, like a bearing analysis and exploration. So let's go back to our analysis worksheet, and I'm going to show you the last part or the feature in this worksheet, which can be, which is the ability to reconfigure my robot's arms or the links. So in this case, using the parameter sweep command, which is available in Maple for MapleSim analysis. I can change the length of the first and second link. However, I'm going to keep the second link the same. So as you can see, the starting and the ending lengths are the same. But for the first link, we're going to select the 0.4 meter and up to 0.45 meters as our varying parameters or varying lengths of that link, and then running this parameter sweep. And you can see how fast it returns back the result. And that's because of the native multi-threading capability of my system, which is already embedded in my parameter sweep command. So side-by-side plots here are showing the angles for one of my joints, which again can be changed. And as you can see here, by changing the configuration or the length of the first link, I was able to kind of reduce the acceleration in some points, and then the characteristics of the motor required for like the first joints have been also changed. However, we should keep in mind that by changing these configurations, we are there is a trade-off. We are changing the loads from one point to the other point. So maybe we are improving the characteristics for one of our motors, or we are lessening the requirements, but we should check for the other motors and see what's going to happen to those joints. And again, that's another very useful feature for designing your motors and the as a part of the robot or machine design process. Thank you, and that was the part I wanted to cover. I'm gonna give back the presenter control to Orang.
Okay, thank you very much, Upton. That demonstration that you saw in MapleSim touched on some of the points that I mentioned earlier in being able to create the model in MapleSim and create a targeted tool for design and design exploration in Maple. So that was an example that we created using Maple's features and programming language to create those worksheets, those design tools, to interact with the MapleSim model in a systematic way and make it a tool for decision making. So here, at this point, we're going to talk about a case study. We have been involved with FLSmidth US, the material handling division, over a project, a multifaceted project, that one of the machines that we worked on was called a dual truck mobile sizer. So we are grateful to FLSmidth for allowing us to share with you this material at this, in this presentation. So a dual truck mobile sizer used in open mine systems handles raw material and brings more efficiency to the way material is handled. And this system, as you see in this picture, interacts with two ultra-class trucks, and it comes in different sizes. In its biggest size, it can it interacts with 400-ton trucks, and it can handle up to 12,000 metric tons per hour. The way it works, those two buckets or skips get filled by the material coming from the mine through those trucks, and they will rise up and dump the material into the hopper in the middle. So we got involved in the process of the design from earlier stages through providing FLSmidth tools to enable them to quickly evaluate their design and come to answers to their immediate questions a lot quicker than they would otherwise been able to get. So in this project, at least this part of the project that we had with FLS, we talked about, or we investigated the skip system model, the part that raises up the buckets and bring them down, the hydraulics that were involved. We looked at those, created early models to do design verification. And we also look at the possibility of vibration. I'm actually going to show you an early design that's based on the analysis that we have done, got rejected and got replaced by a more robust and improved circuits for the hydraulic actuation system. We have created a tool similar to what you have seen in that simple simple pick-and-place robot for motion profile design. It is very important, this heavy machine that goes up and down, that you design a speed profile that provides the correct timing and also does not have high acceleration. With the system that we have, we were able to calculate dynamic loading on various footings and joints and bearings. The footings were also part of this model. On the skip subsystem, we were able to look at multiple designs and update the model as the designer on the FLSmidth side would change the design and keep updating our model on this side since those models were all fully parametric, and we will talk about them. Then we moved on to the complete system, but first we looked at the chassis, which holds everything together. Again, creating models that were parametric because 3 different classes were being designed in parallel. And we had models that could switch from one to another based on the same basic structure. We looked at the weight distribution. You can imagine there are many heavy equipment and parts are attached to this big chassis, and having a handle on the weight distribution and where the center of mass is important. And we also even looked at the deflections and natural frequency of the chassis. This quick calculation that we were able to do was very important to get quick answers to questions before a more elaborate finite element type analysis would come into play. Then we did full system simulation, where we looked at the interaction of the skip loading and moving them in different speeds and different phases, and what it would do to the force that gets transmitted to the ground. In this case, this mobile system would be installed near the mine on potentially oil sands, for example, and that interaction needed to be carefully investigated, so we were able to also provide models that give them the first pass answers to very important questions. And then even for the trucks that come near the skips, because they dump directly into the skips, it is important to have a safety barrier, and we did a little bit of work on that to give some estimate of if the driver, for some reason, doesn't stop the truck at the designated point and hits the barrier at full speed, which is about, for this type of trucks, around 12 kilometers per hour, what will happen? What type of forces are we looking at? Okay, so let's look at some more details of this project that we have been involved with. Here we see the skip system going up and down in MapleSim. You see, similar to the plots that you've seen before, we can plot versus angular time, the forces and the hydraulic pressure that goes through, and these are invaluable information for the designer when they tweak and adjust their design. The model was, as I mentioned, is fully parameterized. There's a multitude of parameters that were incorporated in there. And as I've mentioned earlier, this is an example of a multi-domain system which included mechanical, control system, and hydraulics. Similar to what you have seen, we have created specialized tools. In this case, is a tool that was created for the skip subsystem, which is a parameter sweep worksheet. Would give the designers on FLSmidth side the ability to quickly check different design parameter ranges, change various geometry or other configuration of the model, and compare the results. Even we created a tool to design the speed profile so that they can select the right speed profile such that it has the right cycle time, but also it creates the acceptable level of acceleration both in translation of motion of the jacks, because the flow of oil is a constraint, and also the angular velocity and acceleration of the skip. So this tool became very important in answering those design questions. As I mentioned, one of the earlier designs that we were able to put quickly together in MapleSim and give a validation of the concept was this hydraulic system that you see, which would command the skip up and down and also provide regeneration of the accumulator pressure when the skip was coming down. One of the concerns that got evaluated by our analysis and being able to go from a MapleSim model to a rigorous mathematical approach was the issue of vibration. We were able to use Maple, a mathematical and symbolic capability, to linearize the model, look at the eigenvalues, and look at the possibility of vibration. So we have found that depending on where the sensors are located or how the information are coming in and the controller is tuned, there could be possibility for vibration in the skip motion. And as I mentioned, this design was rejected and replaced with a robust system. So we have now, we are now looking at the system putting together. We have two skips and a chassis system. You can see the blue boxes represent the pressure at different footings for the chassis and the skips. They have separate footing system, and it's important to have the correct force distribution. So our parametric model would go step by step with the changes that were coming down from the designers and enable FLSmidth to quickly know how those changes are affecting the interaction of the DTMS with the soil. And you can see on the plot on the left-hand side, we could plot over time the force distribution, and even with implementing a nonlinear representation of the oil sand, give an estimate of how much sinkage each foot will have over time, and then extrapolate that to even longer times. Here's the structure of the MapleSim model. It's a bit more complicated than the model that you have seen in Optin's presentation. Has different subsystems. The mainframe, the skip system that were borrowed from the other model that we just looked at, footing mechanism, and nonlinear interaction with the soil that got added at each footing location. This model or variation of it were used for model analysis, were used for updating the system quickly between the designers and the people who interacted with the model, including us at the application engineering group here at Maplesoft. And we have created a specialized tool that would just look at many, many mass points that were parameterized on the chassis and quickly calculate the center of mass. One of the things that we were able to do by quickly or simply introducing flexibility into the model based on the dimensions of the system, we were able to validate our model against more complicated finite element calculation, and for the first few modes that were most important, get an acceptable level of accuracy. Using the base model that we had, we also were able to provide answer to the question of what would be the impact loading on the hopper as the skips would dump their content onto the hopper. And we have created, in the same environment as the base model, specialized extensions to the model that would incorporate the flow of material in a simplified, discretized way, and be able to measure the impact force over the duration of that the material is being flowing to the hopper. As I mentioned, the trucks back towards the skips, and there's a barrier in place. It was important for that barrier to also be designed properly, so just in the case of a mishap and the driver doesn't stop the simulation, doesn't stop the truck, the barrier would withstand the loading, and we did a simulation for that as well. This model enabled them to vary the parameter of the truck. There are two different sizes of ultra-class trucks that would interact, and use this tool to get an accurate estimate of what is the force being applied and in which direction onto the choke that stops the motion of the truck. We also incorporated the relevant information in our truck model, such as the suspension mechanism, the damping, nonlinear damping of the suspension, even the nonlinear effect of the tire deformation for a quick but useful estimate of the forces that were applied. Okay, so that was the case study. I'm just going to wrap up quickly. We have talked very little about the third part of our the cycle of engineering solutions, MapleSim, and connectors. Connectors is where we create code from our system, and one of the things that provides that high quality or very optimized and fast code that we generate also provides the option to incorporate the subsystem model from MapleSim into other products such as Altair Multibody or FLSmidth. This will bring together the benefits of using MapleSim and Maple together with other softwares in your tool chain. Just want to mention that here. Just a recap, system level model used for simulation, exploration, and verification, as you have seen in the examples. Detecting design issues, we showed you an example of that with that system level model right off the bat, you can detect the design issues very quickly and have a solution for them or change the design. By bringing all multi-domain parts into the same environment, you improve the product quality, and with this intuitive and physics-based environment, you will have fast iteration and minimize the number of prototypes that you might otherwise need, which translates to shorter time to market.